Hello everyone and welcome to this Abaqus tutorial. This is a basic introduction to Abaqus, and we will learn how to use the main tools and modules through simple example of finite element method. So let's get started. First, let's start with our Abaqus user interface, and we have the starting screen. You can see the starting screen. You can see start session. You can select with standard explicit or with electromagnetic model. Let's exit this window and go to the main window of our Abaqus, the main interface. We have Abaqus 2022 version, and let's start to use the main tools of and modules of our Abaqus CAE. First, before we go to create part and run our and finite element model, let's first go to set working directory. Let's go to file, set work directory, and create your own working directory. Let's go to the D partition, YouTube folder, double click on it, and you can create a new one, create new directory, and add a name to our directory. Click OK. Now we have created introduction directory. Let's select and click OK. Now let's set this directory as a working directory. Click OK. After do that, you can save your Abaqus AE and as a name and add a name to your Abaqus model. For example, let's name it as intro 1 with model extension CAE extension, and in the model save it in the created directory introduction and click OK. Now, as you can see here, the model database is created in the YouTube introduction slash intro.cae. Now, let's take a look at our directory. You can see introduction and your saved CAE file and journal file in introduction directory. That means all files of our CAE project saved in this specific directory. Now, let's start to go through all necessary steps to use it in Abaqus to run your FEM model. Let's get started. In this model, the part module, we will create our part by going to creating part icon and click on it, and you can see your this window and add a name to your part, for example beam, and you can select modeling space. We will use 3D, and the type of our part deformable, discrete rigid, analytical rigid, or Eulerian. We will use deformable, and we will also use the solid and extrusion type, and also we can add approximate size of our part and click continue. Now in this section we will see the main tool to create sketch, the main tool in Abaqus to create sketch and create your part using this tool. First, let's create rectangle and select and create two points, the first point and drag to the second point, and we will have a rectangle. And let's add dimensions. Let's add 200 millimeter in the length and 25 millimeter in the height. You can use this icon to auto fit your view and see all parts inside viewport. As you can see here, we have many tools in Sketch module to create sketch in Abaqus. You can create points, line, circles, rectangle, and many tools. And you can use, for example, create construction line, also use project edges and offset curve and delete or trim tool, and also remove and gaps and overlap. And you can also use linear pattern or circular pattern. We have two options, and also create mirror, copy, and you can and scale your sketch. You can translate your sketch, rotate your sketch, scale your sketch, mirror your sketch, and also you can auto constraint. And we have many options to create constraint in your sketch. And we can also use auto dimensions, and we will have the add dimensions with your manually. And now we have undo last action and the previous redo to the last action, and we can use remove or delete to erase unnecessary edge or erase line. And also you can add sketch or save this sketch. You can save this sketch in your model. For example, save sketch as sketch 1, for example, rectangle. And now you can open this sketch. For example, as you can see here, we have saved sketch in your model. Now let's go to click done, and let's add the depth of your beam. For example, also 25 in the depth of your beam, or to 20 millimeter, and click OK. Now you have our beam. We have our beam in our model created using Abaqus tools. Now let's go to create partitions in our part using create partition tools. First, let's create the datum plan to create partitions. First, let's go to create datum plan. From offset plan or from offset from principal plan, you can, for example, use these principal plans to create datum plan, but we need to create datum plan using offset from plan. Click on this icon and select this plan to create datum plan from this plan. Let's enter value and flip direction to create plan and click OK. And let's add offset value to create plan. Let's for example add 10 millimeter. And as you can see here, we have our datum plan created in our part. Let's create second datum plan from this face. Let's click on this plan, select enter value, click OK, and also we'll use 10 millimeter as a distance of offset. As you can see here, we have our created datum plan. Now let's go to create partitions, create partition, select cell, and use datum plan to create partition. And the first time when we have just one cell, you can select directly the datum plan and create partition. Now we have created partition and we have two cells in our part. Let's go to the second partitions and select cell where you need to create partition and click done and select the tone plan and create partition. As you can see here, you can create partition using many tools. You can use, for example, use edges, or you can create partition in edge, for example, by parameter location, parameter select midpoint, or use the tone plan to create partition in edge, or you can make partition in faces using sketch or the tone plan or many tools. And also, as we make in our part, we can use create the tone plan using define cutting plan, or use the tone plan created, or extend face, or many tools we have. And now let's click done. And now we have a necessary partitions in our part. And now let's go to the next step. In this section, we will create the mechanical behavior of material used in our part. Let's go to create material, add a name to our material. For example, let's use steel material. You can add description, and you can see your material behaviors in this section. And now let's add my mechanical behavior or material behavior. We have many behaviors you can add to your material. For example, you can use general, you can use density, for example, or you can use user output variable, you can use defined file or user material, you can define your own material behavior. You can also, we have mechanical behavior, thermal behavior, electrical magnetic behavior, and others. We have many behaviors used in our, you can use in Abaqus. Let's go to the simple one. The simplest one is the elastic behavior. In the mechanical elasticity, elastic, in this section, you can add the Young modulus to our material, and add also the Poisson's ratio. The units in our Young modulus is in the megapascal, because we have the dimensions unit is in the millimeter, and the stresses and constraint is megapascal. Now click OK. Now we have new material created in our model. The next step is create section, and add a name to your section, steel section, solid homogeneous. In our case, click continue and select material. Because we have just one material, this material selected by default, and click OK. Now we have a new section created in our model. Let's assign this section to our part. Click on assign section, select part, click done, and assign this section to our part, and click OK. The next step after creating our property and assign to our part is the assembly step and create instance. Let's go to create instance. You can select your instance you need to add in assembly and click apply. And now we have our part or our instance add in your assembly. Because we have simple model, we have just one part, we don't need any other steps or any other option to create assembly. In this step, we will go to the step module and create analytical step, and let's go to create step. Go to create step, click on this icon and add a name to your step, for example static step, and we have the initial default, and you can use and choose one of these many steps in your step module. We have dynamic analysis step, static analysis step, and geostatic step, heat transfer step, mass diffusion, and many other steps in Abaqus module. Now we will use the static general step and click continue, and let's add some options. You can use basic. We have nonlinear geometry because we have the just elastic property. We don't need you to use nonlinear geometry. Set to on. Let's take off, take it as is, and you can use the time period of our analytical step, the time of step, and you can use also increment and others option. Let's take this step as is and use the default parameters and click OK. Now, as you can see here, we have our step. You can edit this step, or you can replace by another step if you need to change this step, or you can rename, delete, or use nonlinear and set to on. We have many parameters. Now let's go to file output manager and edit the file output one. Click on edit and select which variables you need to get in your output database. For example, in the stresses, you can select mice stresses or select many others options and variables you need to get in the stress. We have also strain. You can also select displacement, forces, and property in the contact. Depending to your problem, you can choose your variable outputs in the database, in the output database. This variable evaluated through processing by Abaqus. Click OK. Now let's go to the next step for creating Abaqus model. The next step is the interaction step, but in our case, we don't need any interaction options in our part. Let's ignore this step, for instance, and go to the load step and create load and boundary condition in our model. The first boundary condition is the limited movement in the initial step. You can use symmetry, anti-symmetry, inquester, or use displacement rotation. Click continue and select these two faces in our beam model. Click done and use the boundary condition and use the limited degree of freedom. You can use all and select all these degrees of freedom and click OK. Or you can change and allow rotation in this direction. You can use propagate and use this boundary condition is propagated to the static step. to the next step, you can edit in this step, edit your boundary condition. The next boundary condition is our load to our beam. Let's go to create load. In the static step, mechanical load, we will use pressure, and we have many type of our load, mechanical load. We have concentrated force. You can apply moments to our beam. We have also pressure, shell edge load, surface interaction, pipe pressure, body force, line load, gravity, bolt, and many others load. And in mechanical category, we will use pressure. Click continue and select the surface. You can see and read the message. Select surface for the load. You can select this face, this, and this, and click done. And now we will apply our pressure equal to 1 megapascal to this surface and click OK. Now let's go to the next step. The next step is mesh module and create mesh to our part and assign mesh to our part. The first option is to set the size of our elements by going to seed part instance. Let's go to assembly. Let's select part. Go to seed part instance and approximate global size. This value is the size of our mesh. We will use, for example, 2 millimeter in the size of our mesh. Click OK. Click OK. You can also use seed by edges. You can assign mesh to our part by edge, for example. And now let's assign mesh to create mesh to our part. Click yes, and now we have meshing our part with size element equal to 2 millimeter. Now let's go to assign element type. Select the wall part, the wall mesh of our part. Click done, and now let's take a look at these options of our mesh. We have element library, we have standard and explicit. We will use standard because we have static analysis step. We will also 3D stress. We have linear elements. We don't need to use quadratic because we have linear parts. We have linear geometry. We can also use reduced integration, and we don't need to use any of these options because we have elastic property. We don't need to use hybrid formulation or improve and visualization and uncompatible mode. We don't need this option for now. And as you can see here, we have the type of element equal cubic, 3 dimensions, and 8 node, and with reduced integration. You can deselect reduced integration, and you can see this type of node. We have 8 node with linear break. You can click OK, and now we assign element type with element type is C3D8 node. You can use this option to verify mesh. Click verify mesh, select wall part, wall mesh, and you can see errors and warning, and click headlight. As you can see here, we don't have any errors and warning in our mesh. We have great and perfect mesh, and we don't have any warning and errors in our mesh. The final step in our case is create job and run our processing. Let's go to the job module and create job. For example, job 1 or beam 1. For example, add a name, click continue, and now you can use parallelization to select and add the number of your process you have in your machine. You can select your or add the number of your processors in your machine in this step, and you can use graphic acceleration, use your graphic card, add to your calculation, and now let's click OK. Now we have created job. The first step is you can write input. For example, click on write input, and we have input file with the beam1 name. You can see this file in the working directory. You can go to the introduction, the working directory, and see your input file. You can see this file. Let's take a look at this file. This is the input file to the processing step, the step of processing your model, and this is the input to your process. All steps we do in the previous is write it in this file as input data. Now let's return to our Abaqus interface, user interface, and the first and the second step you can use data check to check if you have any errors in your model. Before we go to the running, you can check your model if you have any errors or warnings. Running check. This operation takes time depending to your geometry and complexity of your model, and also depending to the number of elements in your model. Now we have completed check. Let's go to continue our processing and click OK. We have submitted our job, and let's wait time until completing this analysis. Running status. You can click to monitor to see the processing steps, and we have just one step and one increment, and we have completed with this successfully. We have completed analysis and completed job. After completing the job successfully, let's go to the result and see our output database. You can see here we have output database beam1.odb. We have the first look of our result. This is undeformed shape. Let's plot the deformed shape of our beam. This is the deformed shape, the plot, the deformed shape of our beam. Let's first hide unnecessary edges by going to plot option, select free edges and click apply. Let's go to common option, feature edges, apply. Okay. The first result is the stresses in our beam, Mises stresses. Can you see here our distribution of stresses in our beam? You can choose another variables, for example, deformation or strain. You can use also a reaction force. You can see here the reaction force in the support zone, and also you can use displacement. You can select the magnitude value of our displacement or select displacement in the y direction. As you can see here, we have the maximum value of displacement or deflection of our beam. Let's select the magnitude value of our displacement. You can select also let's go to file out. You can see the real deformation. As you can see here, we have deformation scale factor. We can use just one scale of our displacement. This is the real displacement of our beam under the 1 megapascal pressure. This is the real displacement. For the reason of showing your result, you can decrease your scale to see the information clearly in your format shape. You can use, for example, 1000 to see the displacement clearly in your parts. Let's go to 1 scale, apply. Okay. Now let's create path to plot displacement through the trajectory longitudinal to our beam. For example, let's go tool, path, create. For example, let's add a name path1, select node list, continue, and click add before. Let's show our edges. Select this node, the starting node, and let's go to end node. You can see your path through our beam. Click done, and now we have our path created. Let's plot the result through this path. Go to file output, create XY data, select path, continue. We have the path name, path1, and select the deformed shape, include intersection, and let's plot file output. Go to file output and select displacement in the y direction. Let's click on plot. Let's select project onto mesh, plot, select and deform it. You can see your displacement curve around this path created before, and you can see the maximum deflection in the middle of our beam, and we have zero displacement in the support zone and the maximum deflection. Let's add another viewport. Create viewport, click on it, and tile viewport vertically. We have two viewports, and let's click on this zone and select plot contours deformed shape, and you can see your deformed shape and stresses contours. Let's go to the displacement and select displacement in the y direction, and this is our result. Until now, I hope you enjoyed with this video. Don't forget to subscribe in my YouTube channel and like this video. See you